Previously in class, we've talked about the complex exponential function. Just to review a few mapping properties, we know that the exponential function is never equal to 0. We know the exponential function maps horizontal lines in the complex plane to rays centered at the origin, and that at the origin there is actually a hollow dot. We also know that the exponential function maps vertical lines to circles. Now, in the next few minutes, what we're going to do is we're going to talk about the logarithm, which we believe in some manner should be the inverse of the exponential. So how do we define the complex logarithm? What does it mean to take the log of -1 or the log of I or something like that? How do we define the logarithm? Well, we would like it to have as many properties of the usual logarithm as possible. We would like for e to the log of z to be z. We would like for the log of e to the z to be z. We would like other properties to hold, like the log of z1 times z2 is the log of z1 plus z2, and so on and so forth. Well, it ends up that of these properties, only this one is actually going to be satisfied. When we define the log in a few minutes, this one actually won't be true, and we'll see why. Okay, so every complex number can be written in polar form, but the representation is not unique. For example, let's suppose we consider the complex number 1 plus I. 1 plus I lives up here in the first quadrant. It's a distance of √2 away from the origin. Now it makes an angle of pi over 4 radians relative to the positive real axis, the x-axis. But we could also, instead of going pi over 4 units that way, we could go around -7 pi over 4 units, or instead of just going up pi over 4, we could swing around another 2 pi, 9 pi over 4. So there's infinitely many ways to express a complex number. If we take into account, we can actually go forwards or backwards around the circle as many times as we like. But there is only one way to express this complex number, √2e to the I theta, where theta is restricted to be between minus pi and pi. Theta is greater than minus pi and theta is less than or equal to pi. And the only angle that works for of these three choices and many others is when theta is pi over 4. And this is a true property about any complex number. If we write it in polar form, we can choose a single angle which lives in this range. So to say that again, any complex number z can be expressed in polar form using exactly one angle in the range from minus pi to pi. We don't include minus pi, we do include pi, and we call this angle the principal argument, which we're going to write arg of z. And we use a capital A to emphasize the fact that this is a principal argument. Okay, so this is somewhat redundant, but every complex number z can be written exactly in this form. Z is the modulus of z times e to the argument of z. So in the example above, √2 was the modulus of z, and the argument of z was this angle, pi over 4. Okay, so let's take a look at some examples. One plus I, that's in polar form √2 e to the I pi over 4. That lives up here in the first quadrant, and the argument is that angle pi over 4. 1 minus I lives down here. Now, you might say, oh, well, we could go around 7 pi over 4, but 7 pi over 4 is not in this range. Instead, we have to go through negative pi over 4, because that's within this range. So 1 minus I has a modulus of √2, and its principal argument is minus pi over 4. 3 is the same as 3 e to the 0I. So 3 has a principal argument that's equal to 0 radians, not 2 pi radians, which is outside this bound, but just 0. 4I is up here, way up yonder. It makes an angle of pi over 2 radians. That angle satisfies this property, so the principal argument of 4I is pi over 2. Minus 4I lives way down here. Now, to get to minus 4I, we could go around 3 pi over 2, but that's not within this range. Instead, we go down negative pi over 2. So the principal argument of minus 4I is minus pi over 2. Minus 1 plus root 3I is up here in the second quadrant. It's a fairly easy exercise to show that in polar form this is 2e to the 2 pi I over 3. 2 pi over 3 is in this range, so the principal argument of this complex number is 2 pi over 3. Let's look at minus 1 minus root 3I. That's down here. Okay, in polar form you can express that as e to the 4 pi over 3, but 4 pi over 3 is not within this range, so instead we have to go back minus 2 pi over 3. Minus 2 is over here. Now we can express, to get to minus 2, we could go through pi radians or negative pi radians, but of those two choices, only pi falls within this range because the argument has to be less than or equal to pi and greater than negative pi. So the argument of negative 2, the principal argument, is 2e to the pi I. Okay, the fact that we can express each complex number in polar form exactly one way if we use the principal argument is going to help us define the log. So we want e to the log of z to be z. That's because the exponential and the log are inverse functions. Now let's express z is the modulus of z times e to the I principal argument, and we know that there is only one principal argument. Now we're going to play a little trick. We're going to write the modulus of z as e to the natural log of the modulus of z, and we can do that provided the modulus of z is not 0, because we can't take the log of 0. Now look at these two exponentials. We can combine them into one using properties of exponentials. So we have e to the natural log of the modulus of z plus I times the principal argument. Now, let's take a look at this side. E to this, e to that. It only makes sense then to define the log of z to be the natural log of the absolute value of z plus I times the principal argument. So that is how we, in fact, define the logarithm. Okay? Log of z is the natural log of z plus I times the argument of z. The function is called the principal branch of the complex logarithm, and we use capital L to denote the fact. We don't use ln or anything like that. It's log with a capital L out in front. Now here are some properties. Log of z is defined for any complex number other than 0. The real part of the log can take on any real value of any real number, be it positive or negative. For example, if z was a half, this would be negative. If z was a third, this would be negative. If z was a million, this would be positive. The imaginary part is between minus pi and pi, not including pi, minus pi, but including pi. And that's because this quantity right here has to be between minus pi and pi because it's a principal argument. So this part can be positive or negative, but the imaginary part, which is right here, has to be greater than negative pi and less than or equal to pi. Let's take a look at some examples. Previously, we showed that 1 plus I is root 2 times e to the pi over 4i. Pi over 4 was the principal argument. So that means that the principal log of 1 plus I is the natural log of the modulus plus I times pi over 4. Previously, we showed that 1 minus I is root 2 e to the minus pi over 4i. This was the principal argument. So that says the log of 1 minus I is the natural log of 2 minus pi over 4i. That log of 3, well, we showed that 3 equals 3 e to the 0i. The principal argument was 0, so log of 3 is the natural log of 3 plus 0i, and that's exactly what we want. We want the new log to be the same as the old log for real numbers. The log of 4i. Previously, we showed that 4i could be written this way, where pi over 2 is the principal argument. So the log of 4i is the natural log of 4 plus pi over 2 times I, where pi over 2 is the principal argument. The log of minus 4i. Previously, we showed that this is minus 4i times e to the minus pi over 2i, where minus pi over 2 was the principal argument. So that means that log of negative 4i is the natural log of 4 minus pi over 2 times I. Similarly, the log of minus 1 plus root 3i, because we could write this way, where 2 pi over 3 is the principal argument. The log of that is the natural log of 2, that's the modulus, plus 2 pi over 3 times I. And finally, the log of minus 1 minus root 3 times I is the natural log of 2 minus 2 pi over 3i. And that's because minus 1 minus root 3i is 2 e to the minus 2 pi over 3. So the idea to take the log of a complex number is you have to write that number in polar form, and you have to make sure that the angle you use is between pi and negative pi, using a principal argument. And once you have this, it's fairly straightforward to write down what the principal log is. And finally, the log of negative 2. Negative 2 was written as 2 e to the pi I. The principal argument was pi. So the log of negative 2 is the natural log of 2 plus pi times I. If your calculator is in complex mode, you can actually verify that fact. Now here's the good news. E to the log of z is z for any complex number z. That's how we defined our principal log. The bad news is that the log of e to the z does not in general equal z. Here's an example. Suppose that z is 3 pi I over 2. Then e to the z would be e to the 3 pi I over 2, which is negative I. And the reason is that if we go through 3 pi over 2 radians, we'll be down here in the complex plane at negative I. Now, if we take the log of e to the z, the log of negative I, the principal argument, negative I, is down here. Its principal argument is minus pi over 2. So we'd have the natural log of the modulus of minus I, which is 1, because this has length 1. And then we'd have minus pi over 2i, because minus pi over 2 is the principal argument. Now the natural log of 1 is 0, so the log of e to the z, when z is this number, is minus pi over 2. So it's a difference. We have 3 pi over 2, but minus pi over 2, so you'll notice how log of e to the z is minus pi over 2i, which is not the same as z. So this property, log of e to the z equals z, does not hold in general. But there's more bad news. The log of z is not continuous on the negative real axis, and here's why. Let's say we take a number minus 1 plus 0.01i. Okay? Now, 0.01i is so close to 0 that this is, in essence, natural log of 1 plus pi I. Now, where does the pi come from? Well, minus 1 plus 0.01i would be over here, but in the second quadrant, and the angles go from 0 to about pi, because this is just barely in the second quadrant, the principal argument of this number would be very close to pi, not negative pi, because it's in the second quadrant. Now on the other hand, let's say minus 1 minus 0.01i. That's a point that's in the third quadrant, but barely. And to get to that point, and to keep it within our principal argument range, we don't go more than pi, we have to go about negative pi radians. So these numbers, minus 1 plus 0.01i and minus 0.01i, are very close to one another, but they're basically on opposite sides of the real axis. So those two numbers are pretty close. You would expect their outputs to be close, but their outputs are pi I basically and minus pi I. Those two values differ by pi units. So here's what happens as you walk from the right here to up there in the complex plane. Your imaginary amount increases, jumps by about 2 pi. Anywhere along the negative real axis, there's a jump in the log function. It is not continuous. Okay, and we call that the branch cut. So 0 plus the negative real axis, that forms the branch cut for this function. Let's talk about the mapping properties of the log briefly. The log maps the punctured plane, C without the origin, into the horizontal band where the imaginary part is between pi and negative pi. And this is actually done in a one-to-one manner. F is an injection. And again, the imaginary part has to be between minus pi and pi. F maps rays to horizontal lines. F maps circles to vertical lines. Here's a picture. What I've done up here, I've made one copy of the complex plane. Here's the imaginary axis, here's the real axis. You'll notice that I have a line in green, it's solid there, it's dotted there. I have a line in black at pi over 4, it's dotted here, it's solid there. Down at minus pi over 4, this is actually in blue. Minus pi over 4, dotted, solid. And now at minus 5 pi over 6, horizontal line that's dotted here, and that's red. Now under the exponential function, what happens to each of these lines? Well, this line right here at pi over 4, this part is going to get mapped to a ray that starts on the unit circle and goes out that way. And the angle is pi over 4. So as I walk along that line, I actually am moving away from the origin along that ray. As I move in that direction, I'm actually headed towards the origin, but I never get there. Let's take a look at minus pi over 4. This was in blue. The image of this part is down there. This angle is minus pi over 4. The image of that part is right there. As I stand here and walk in the direction of the positive real axis, my outputs are moving out that way. If I move in that direction on the negative in that direction, my outputs are actually moving towards the origin but never getting there. Now let's take a look at pi. If I go through an angle pi, I have what I see here, that's green. As I move in that direction, I move out this way. As I move in that direction, I'm moving towards the origin. Those are green hash marks. Down here at minus 5 pi over 6, this is mapped to this. As I move in that direction, this angle is minus 5 pi over 6. As I move in that direction, I move outwards. As I start and move outwards, I move inwards here. So that's what the exponential is doing. So the log, which is the inverse, is doing exactly the opposite. The log is taking this ray and is mapping it up here. The log is taking that segment and it's basically mapping it right there. The log is taking this dotted segment and mapping it to wherever I have the green, which is up here. It's mapping this solid line to that solid line. So the log is going to be mapping these rays to horizontal lines. This is the unit circle. Any point on the unit circle has a modulus of 1. A modulus of 1. And the natural log of 1 is 0. So the unit circle is going to will get mapped to the imaginary axis. We will discuss these mapping properties more in class. Here are some things for you to do. Calculate the exact values of each of the principal logarithm branches.